Welcome to this presentation about practical and useful information for model railroaders about DCC and Basic Electric. No matter if you are a beginner and new to a hobby, new to the DCC system, or an experienced model railroader, we hope there will be something for everyone. So let's get started. Here you can see the presentation's contents. And here is the timetable in minutes, making it easy to navigate through this presentation. DCC, Digital Command Control, has been around since the beginning of the 80s, so it's well established. All major brands in model railroading has products or support for DCC, even if the different brands have their own solutions and products. It is one standard on the track. Locomotives from one vendor will work on another vendor's DCC system. Let's see which components that build the DCC system. Throttles is where you control the system. It could be from an app on your smartphone or iPad. It could be from a built-in touchscreen or in another wired or wireless control unit. There are several throttles available on the market. The throttle is communicating with the command station, the brain in the system, where the DCC commands are created. The command station is sending the DCC commands to a booster. The booster is boosting, amplifying the signal and delivering it to the track at the desired voltage. Throttles and command stations are low voltage digital products, typically 5 or 3.3 volt. That's why a booster is needed to amplify the low voltage into voltage on the track that locomotives can use. You will find several systems on the market that has throttle, command station, and booster combined in one unit. Accessories like electrical turnouts, LED, lightning, sound, and signals can also be controlled from the command station and throttle. The command station is connected to accessory decoders, either wired or wireless. Your locomotives receive the DCC signal from the rail, decode the signal, and controls the locomotive speed, direction, light, and sounds. The DCC signal controls both the DCC code and the power for running the locomotives. Before we continue with more DCC stuff, I want to take you through some very basic electric, an introduction that will be useful to know when you need to plan, buy, and install different kinds of electrical products on your layout. For the experienced users, it could be a fresh reminder about the basics, or you can skip this section. Water analogy to electricity to simplify the physics. So voltage is the water pressure pushing the water. Bigger pressure can move bigger things, like higher voltage can drive bigger electrical motors. Current is the amount of volume of water that's flowing per second at a certain pressure. Resistance is a blockage in the flow of water, like you are standing on a water hose. Less water and pressure is coming through. What builds the pressure, volt, is the difference in levels. In this water example, the left tank with a lot of water will fill up the empty tank to the right. It is one of the very basic physics in nature, level out difference to equilibrium.
To describe the result, the effect of a volt and ampere doing a job together, we are using watt. How strong and fast the water will spin, or how bright the light bulb shines is all measured in watt. Like a pipe or hose is leading water, we need a conductor that lead the electricity, that have the ampacity capability to carry the number of amps without overheat or burn up.
Planning and installing wires on your layout, it's very important to select the right cable. This table contains both the measurement in AWG used in US and square millimeter that is used in Europe, and how much the current a certain cable can carry. To get the right dimension of a cable, you need to put in more values than just the amp. Factors that matter are: what kind of conductor will be used, copper or aluminium? A big factor is how long the cable is going to be, what voltage and amp the cable is going to handle, what temperature and how much drop in voltage that is accepted. Let's look at two examples. In the first example, we're using a 5-meter long cable with maximum voltage drop of 2%. In the second example, we changed the length to 1 meter and allowed a voltage drop of 5%. The difference in what cable that's needed is big. 11 AWG, 4 square millimeter to 20 AWG, 0.5 square millimeter. I would recommend that you use a cable calculation tool available on internet when planning your electrical wires. OFC, oxygen-free copper, cables used for hi-fi speakers is a very good choice when installing the bus wires. Always make a cable wire drawing and make sure that every cable has an ID. Mark the cable with that ID. Keep the cable installation neat. It will be crucial the day when you are troubleshooting an electrical problem. I will come back to the part protecting your boosters and decoders later in this presentation. And of course, document the installation. Even if you remember everything the day you are installing the wires, a week, month or year later, you'll probably forget a lot of the details. The better the cable drawing is, less work you will have with documentation.
Now, just a small introduction to some very basic components that are often used on the metal railroad. As we talked about before, a resistor is easy to understand, used to make resistance. And there is a lot of different types of resistors, but we won't go through that now. One of the most used resistors on the layout is the common carbon or metal film resistor, often used to limit the current and voltage levels to an LED. Even if the LED have a defined current rating, for example 20 milliamp, it could be too bright. By using a resistor with a higher resistance, you could lower the current to 10 or 5 milliamp and get the brightness you desire. We won't go into details for the other components. This list is just an introduction, and if you're interested to learn more, there is a lot of information available on internet and YouTube. Here you can see a list over electrical symbols and reference SI prefixes used to represent very big or very small quantities. Observe the difference between the letter M in uppercase, that stands for mega, while in lowercase it stands for milli. When calculating with different prefixes, it's always good to convert it back to the basic unit to avoid miscalculations. For example, 100,000 microamp is the same as 100 milliamp, and that is the same as 0.1 amp.
So what is needed to make electric current to flow? a electric flow and a complete path. In this picture, electricity is flowing from the battery negative side minus through the bulb to the battery positive side plus. If we didn't have a bulb with a resistance, we would have a short and quickly empty out the battery. In this picture with the LED, we have the same flow as for the bulb, but the resistor is limiting the flow of current and voltage to a level that suits the LED's specifications. Otherwise, the LED would burn up. All elements in an electrical circuit, like the bulb and LED, heat up when the current is crossing. We could replace the bulb with a resistor to complete the path and to avoid a short, but it would make no sense to just have a resistor. Polarity in electricity defines the positive and the negative charges. For a component in a conventional current, the flow is going from positive plus to negative minus, but the electron flow is opposite, from negative minus to positive plus. The electron flow is, however, not really something that model railroaders need to pay attention to. But if you hear discussions about who is right about the electrical flow, you can say both, depending on what flow they are describing. Anode and cathode is also something that can be good to know something about, without going into a lot of physics. A node is many times the positive and cathode is the negative. But not always. That depends on the cell type. It is the sign plus and minus that indicate that. The LEDs is having a positive anode and the plus is indicated by the longer leg. Ohm law, the famous triangle, is very simple to use. The upper horizontal line represents division and the lower vertical line is representing multiplication. Just cover the value that's missing, then you will see the formula needed to get it. For example, to calculate the resistor needed for an LED, we know the voltage and current that's for the LED, like 3 volt and 20 milliamp, and I want to connect it to my 12 volt output. How big should the resistor be? Start by taking the 12 volt minus the 3 volt for the LED, gives us a 9 volt difference. Then divide the 9 with 0.020, that is 450, so the resistor should be at least 450 ohm. If we are using the same triangular values, put P, the watt, in the top instead. We will get the result of 0.06 watt. VA, volt amp, is volt multiplied with amp to get the total power. There is an analogy with beer. If you fill up a glass of beer, the liquid in the glass is amp, but the liquid and foam together is volt amp. Alternating current is what comes out of our outlets because it's easy to produce, easy to transport over long distances, and easy to transform up or down. In the US, 120 volts 60 Hz, and in Europe, 240 volt 50 Hz is used. AC is great for heavy loads like oven, heaters, washers, and so on. But AC is not working with digital signals. They need a stable and steady voltage. So DC, direct current, is needed. All batteries is also only DC. But wait, I heard that DCC and AC, almost DCC is a DC voltage that has been modified to a square wave that looks like AC, but it's not a AC sinus wave.
Nice timing. Now it's DCC time again. As mentioned before, the DCC signal is generated in the digital low voltage computer world and passed on to the booster. The DCC signals digital 0 or 1 is encoded in polarity changes length, called phases. By using two voltage levels, instead of having the traditional single level 0 and 5 volt, is making the DCC signal much more resilient to disturbance. The signal is building the DCC packet, the DCC protocol containing address and instruction, to what we commonly call the DCC command. Both the encoded DCC code and power to the train is in the same electrical signal that passed on to the track. M-scale is typically using 12 to 15 volt, and HO scale is typically using 14 to 18 volt. Higher voltage to the track is not always better, because it must be rectified and adjusted to the locomotive's DC motor. The voltage being wasted during this transformation down will be heat, and heat is no good in small n or HO locomotives. The DC command is decoded into the locomotive's DCC decoder. We can adjust and customize the decoder's behavior through its CVs, configuration variable. NMRA defines up to 1024 different CVs, and each CV is an 8-piece register where we can adjust locomotive's behavior like acceleration, speed, sound, and so on. How many settings you can make is determined by the decoder. A multimeter won't give you exact voltage reading from the track, but you can use a multimeter to check so you don't have any voltage drop between the track joints. To get an exact DCC voltage reading, you need to use an oscilloscope or a DCC measurement instrument. To ensure that the track having as good electrical connection as possible, it's a very good idea to solder the outside of all the track joints. McLean of Sweden have a nice YouTube video describing how this is done.
How much current you can take out from the outlet depends on how many outlets that's sharing the same electrical phase and what's already connected to the phase. Normally the AC load, it is not a problem if you don't run a very big layout. It is easy to convert the AC current to watt to see how much load you can put on the outlet. In the US, we have typically 120 volt multiply with 15 amp will give you us around 1800 volt. In Europe, we have typically 240 volt multiply with 10 or 15 amp will give us around 2400 watt or 3600 watt to use. The AC alternating current needs to be converted to DC, direct current. The best way to use switch mode power supply because they are very effective and normally include electricity protection. The voltage output needs to be precise and stable to the specified input requirement. The current needs to be at least what required but can be higher. You could put a 100 amp power supply outlet to 1 amp input. No damage would be done, but 99 amp would be unused and probably just a waste of money. To know when an extra booster is needed, just summarize the number of locomotives that will be running at the same time and multiply with around 1 amp. Then decide how many turnouts that could be active at the same time and multiply that with 0.5 amp or 1 amp depending on the turnout's age and condition. Avoid to have anything else connected to the track that require power, but if you do have other devices connected to the track, you need to add the current. The sum of locomotives, turnouts, and eventually other components Current is the number of amps that the booster needs to deliver. If more amps is needed, then you need to install an extra booster. Power districts. Divide your track into sections, power districts. Isolate from each other. Inside each district, you can have as many feeders as you want to avoid power drops and handle blocks. Connect the booster's output to the power districts. Connect the booster to your command station data. Also use a common ground to all the booster and the command station to avoid ground loops. Connect the booster to its power supply, positive. Use the same brand on the boosters as you have on the command station. It could work mixing brands, but many times you will experience trouble doing it.
Feeding the track. In this table, you can see that the track heights or the track code has an impact how good the track is to leading the power. Thinner track needs more feeding to avoid power drops. Most downscale is using either code 80 or Kato Junior track. Feeding the track every meter here should be a good choice. The bus wire should be either a twisted wire or a low impedance wire. A good choice of a cable is a HiFi oxygen-free copper OFC speaker cables. Avoid longer bus wires than 30 feet, 9 meters, because the DCC signal's quality will decrease. You will absolutely want to protect both your boosters and decoders from being electrical damaged. The first thing you can do is to disable analog operation on each locomotive's decoders. This is because of a power spike could in some cases be perceived as an analog current and make the locomotive to run away. To disable the analog operation, you're using bit 2 with a value of 4 on CV29. CV stands for configuration variable, and each decoder can be adjusted through the CVs. This is called the programming the decoder and should be done on a separating programming track. We will not cover DCC programming further in this presentation.
To protect the boosters and decoders, many have installed DCC circuit breakers. Even if the command station has a built-in circuit breaker that shut down the entire DCC system if a short is detected. By installing separate and quicker DCC circuit breakers that just shut down the power district that is affected, the rest of the layout could continue to work normally. By installing RC snubbers at the end of the bus wire, you suppress voltage spikes and ringing in the bus wire. Absorbing bulbs like a 12-volt car bulb can be connected to the booster's output to reduce, absorb high current, a simple and effective protection. You will find YouTube videos describing the technique. TVS diodes can be installed both on a locomotive's decoder and to specific track sections that are problematic. You will find YouTube videos describing the technique. If you're only running a smaller layout with only one power district, the command station's built-in protection could be enough, maybe adding a bulb protection.
Assigning blocks to your layout. Blocks is used to enable automation and train signals, to let the system know if a section is free or occupied. How do we do that? Divide your layout into the number of sections you need. In this picture, 4 sections, blocks, is used. Each block should be long enough to carry your longest train set. Isolate the blocked electrical in the joints or in the outgoing track from a turnout. Then add feeders to each block. Install either in and out sensors or a block sensor to each block. If needed, separate position sensor or refit sensors can be installed inside of each block. Connect the sensors to accessory decoders that communicate with your command station, wired or wireless. And make sure there are at least one block free from trains to avoid deadlocks when automating.
All these accessories and maybe more is that you will find on many layouts. The accessories connect wired to the nearest DCC accessory decoder in the picture marked with the green arrows. The accessory decoder connects to the command station, either by a wire or wireless. Here marked with the red arrow. If multiple accessory decoders are installed by wire, they normally connect daisy-chained after each other. DCC commands is sent from the command station to the accessory decoder that handles the accessory in the picture marked with the orange arrow. If a sensor is attached to the accessory decoder, the data is sent from the accessory decoder back to the command station. See the blue arrows. Here you can see different types of popular command stations. To control an accessory or train, manually use the throttle. If you want to integrate automation, then you normally connect the command station to a computer, wired or wireless. Some of the command stations have included functionality to automate directly from the command station, but they are more limited than the computer software. Example of popular automation software are JMRI open source license, nowRail open source license, Train Controller commercial license, iTrain commercial license. There are other automation software on the market. This is just some examples of the most popular. WICS is a shortness for Wireless Control System. It's a new project started fall 2025. It's an open source non-profit project that consists of both hardware, PCBs and software to make the installation and configurations easy as 1, 2, 3. The foundation is based on ESP32 microcontroller and nowRail that use the ESP-Now communication protocol. Fantastic functionality, but not so easy to use or install. You need to understand Arduino IDE, C, C++ programming languages, libraries, and compiling. The WICS software adds simplicity so that the nowRail can be used by people that isn't interested in C++. One-click installation instead of compiling C++ code. WICS also adds hardware, PCB, printed circuit board that are customized to be installed on the model railroad layout. You only mount the components on the PCB that you are going to use, even if the board may have more connectors or functions on the PCB. They can be left unmounted through the board's modular design, saving money. Every board PCB comes with detailed mounting instructions and component list, making it easy to get the boards ready. It is a little bit of a copy how IKEA is selling furniture. Mount yourself, save money. Since it is a non-profit project, it's very affordable. You only pay the real cost for the components and the boards. So what kind of boards is WICS producing? The gateway and controller that connects to your command station. Only one is needed per layout. The multi-board has many connectors, for example, LEDs, servers, sound, relay, function. This board can be a controller in a small installation without sensors. Then we have several tiny one-function boards that is easy to spread out over the layout. You could also buy ESP32 commercial boards, like a relay or soundboard, and then add the WICS software. All the boards only need a 5-volt power wire. Wireless is nice. And of course, all connections to the boards is solder-free, making it easy as 1, 2, 3 to install the boards on your layout. The first boards will be available during spring 2026, and you will find detailed information about the board's functionality as its successfully will be published on WICS GitHub. Thank you for watching this video. Hope you enjoyed it. We look forward to sharing our next video with you. For more information about WICS or to download the presentation in PDF format, please visit WICS GitHub. Until next time.